We have seen many of the important mechanical properties such as yield strength, tensile strength, hardness of the material, and so on, right? But if you see the actual scenario, okay, of the materials, okay, how they fail, okay, for example, upon the application of load, okay, it is rather very complex in nature, okay, simply because the kind of loads that we apply, okay, are not very simple in nature, okay. Of course, in the laboratory, we always assume either load to be tensile, right, or the compressive, okay, or the shear. So very simple, primitive, load cases that we usually assume and try to characterize the material's properties, okay, like the way, for example, yield strength. How do we get the yield strength of a material? We conduct a tensile test, right? And what kind of a load we are applying to the material? We are only applying a typically a tensile test. Of course, we also do conduct a compression test, but usually tensile test, okay, is what very common, okay. But all these are, under the assumption that the load may be applied gradually, right? But in real terms, okay, if you put your metallic component in the, or any material in the actual application, when you put it in the application, what kind of, you have any control over kind of loads that may be applied on it? Okay, it need not be always gentle, or a gradual, or very slow uh, application of the load, right? Rather, it is very random, right? Sometimes it may be a sudden load, sometimes you may be applying a repetition of the load, okay. uh, like cyclic load we call. So it may be again a mixture of tension, compression, okay, a shear, okay, bending. So, and it may be sudden, okay, right, it may be repetitive. So a different types of loads, it's a combination of all this, okay, is what typically the scenario, right? Now, uh, the question is, can an engineer assume the load is applied gradually and design the materials or design the components based on its yield strength alone, or should we actually bother about the real, okay, scenario, okay, such as a complex loading condition, and then design the components to withstand such uncertain loading conditions, okay. So definitely the answer is yes. You have to take care of all these uncertain conditions, okay, uncertain loading conditions, right? Otherwise, the material will simply fail. Okay, the component will fail. Just imagine an aeroplane. Okay, if you assume all the aeroplane components are designed for its yield strength, that means you assume the material will not fail until it reaches the, it's loaded beyond its yield strength. That may not be the case, because you have dynamic loading conditions there, okay. You have fatigue conditions, that is cyclic loading conditions, and you have high temperature, okay, prevailing, that some components may be exposed to very high temperatures, and the yield strength that you would have measured at room temperature may not be the actual measure of the strength of the material. So all these things are there, okay. And to make the matters worse, we also assume the material to be perfectly defect free, okay, when you design a mechanical component, okay, for aeroplane or for an automobile or for household application, or even for some structural, okay, like your buildings and so on. But unfortunately, the reality is none of the component, none of the material is defect free, okay. It is literally impossible to produce a defect free material, okay, in real terms, okay, in practical conditions, okay. When I say defects, material defects, uh, what kind of defects I'm talking about? It may be just a processing defect, okay, like when I do some casting, when I produce it by by employing some kind of a technique, okay, processing technique, manufacturing technique, I may induce a lot of defects, okay, welding defect, all these things. The material may not have joined properly, okay. Yeah, apart from this, okay, all these are actually avoidable defects. What is not avoidable is the microstructural defects. For example, we already discussed in our earlier chapters, we have so many types of defects like point defects. Okay, we have line defects, right? Dislocations. We have volume defects. Even grain boundary is considered as a kind of defects, which can facilitate the grain crack to grow or propagate along. So all these defects are always taken for granted. Okay, that means you always have these defects inherently in the material. You have to live with the defects. Now that means you have to design these materials, okay, assuming this kind of defects, you know associated with these materials. Okay. One of the important parameter we consider is fracture toughness. Okay, where the difference between this fracture toughness, which is a mechanical property of the material, compared to the yield strength, for example, is our assumptions. Okay, in fracture toughness, we assume the material is having a flaw in the sense a defect. Okay, say an opening, okay, in the material. Okay, so how, because we all know typically the material ultimately fails by fracture. Okay, but before fracture, it may undergo some deformation depending on whether it is ductile or tensile. Okay, but ultimately it fails by fracture. So what we now assume is if there is a flaw inside a material, typically that kind of we call it crack. Okay, if it is having a crack, it can easily propagate, right? The crack can propagate and ultimately it will lead to the fracture of the material, right? So now, can we have a measure, okay, for a material, what is its resistance for this crack to propagate within the material and fail the material by fracture? Okay, that actually measure is nothing but the fracture toughness. Okay, so the fracture toughness measures the ability of a material containing a flaw to withstand an applied load. Okay, that's what is written here, right? So assuming then the question is how you measure. For example, yield strength, we measure it by conducting a tensile test with a gradually applied load. Okay, but here fracture toughness we actually measure say by having a specimen, okay, something like this, and typically giving a predetermined a known sized flaw. Okay, we induce it artificially. For example, this is a crack, you can see at the edge. Okay, either at the edge or at the center, that is internal, this is external. Okay, surface crack. Okay, you can have either configuration, one specimen, okay, with a flaw like this, okay, of known dimension. If a is the dimension, if it is edge, you consider it is 1a. If it is internal, you have to consider it to be 2a, okay, size. Okay, and what you will be doing, you can apply either tensile load or compression or shear. That means these are the different modes, okay, of load. In each mode, it may fail differently. Okay, for example, very interestingly, if you have a compression load, okay, then this notch, okay, or this crack may not actually propagate so easily because the loading is only compression. That means there is no driving force for the crack to grow. Okay, but whereas if it is a tensile load, okay, that means essentially you are raising the stress at the corner, and essentially this crack will grow, propagate into the material and finally leading to the fracture of the material. So in our case, we assume we are conducting a tensile uh, by using the tensile load. So how the material withstand the load? Okay, at what point the material will fail? Okay, that we will consider to be the fracture toughness. Okay, to be precise, we have something called stress intensity factor. Okay, it is nothing but it is given with this formula, like F is nothing but it is a factor, geometry factor. Okay, and it depends whether it is this factor depends on whether the fly is internal or the fly is uh, you know if, at the edge. Okay, for example, if it is internal, the fraction, the f is taken as 1, whereas if it is at the edge, it is taken as 1.12. Okay, right. Similarly, sigma is nothing but the load that you are applying, in other words the stress. Okay, the stress that you have applied, and of course A is nothing but the size of the notch or the size of the flap. Okay, and you will be getting the stress intensity factor. That means the locally how much stress, okay, it is experiencing at the flap. Okay, because that we call stress riser. Okay, the stress concentration at the corner of this will be much more than what you actually apply here. Okay, yeah. Now, what is fracture toughness? Okay, that is given here. So you keep applying the tensile stress, okay, until the material fractures. Okay, because there is a point at which this particular crack will propagate and the material will fail, right? So that is the critical stress intensity factor at which the material is or the fly is growing in size and finally causing the failure. That critical stress intensity factor is what we call fracture toughness. Okay, and this fracture toughness, as I said, will be of different modes. For example, in our case, what we mentioned is tensile. That means we call it K1C. Okay, it is the one means first mode. First mode is tensile. Okay, if it is shear or if it is in other configurations we call it 2C, 3C, and so on. But essentially, all that you have to understand is there are different modes of failure by fracture, and one of them is by tensile, and the stress intensity factor, the value of stress intensity factor at which the material fails by fracture by the growth of the crack is what we call fracture toughness, right? The next important criteria for failure is fatigue. Okay, fatigue, you all know, the literal meaning of fatigue is when somebody is tired, we call he's under fatigue. Okay, that means you would have done not so much of work, or not very very unbearable work, but you would have done some work of less load, but doing it again and again. If we call it monotonous, right? Similarly, if you do the same thing again and again, what happens? You get fatigue. Okay, you'll be tired. Okay, the very similar thing is what happens with the materials also, which are having no life, but still they undergo fatigue, and they exhibit fatigue failures. Okay, that means they are not, you are not applying the load to the extent of yield strength or to the extent of fatigue, to the extent of tensile strength and so on. Okay, you may be applying lesser load. Okay, but even then the material fails. How come? Because you are applying it repeatedly again and again and again. Okay, it's what we call cyclic load. Okay, so the failure of material, even though you haven't applied a critical load. Okay, that means you have, even though you haven't applied the load beyond its yield strength, material still fails under repetitive stress conditions. This is what we call fatigue failure. Okay, so most of the components, okay, which are under dynamic load, okay, are the components which undergo some extreme loading conditions. Okay, like for example aeroplane, okay, components and so on. Okay, these are all designed for fatigue strength. Okay, not for the yield strength. Okay, because you all know, as I said, what happens, the material may fail even below its yield strength if it is undergone a fatigue. Okay, so now let us see how we quantify fatigue. Okay, even before that, you can see the types of loads that we may have. It is a cyclic load. Okay, that means you have positive tensile compression, like it's a reversal of load. Okay, similarly you may have all positive, all tensile load, but change in the load amplitude. Okay, or it may be completely a random load. Okay, in all these cases you are applying actually a cyclic load. So in fatigue failures, what happens? Initially you will be having a tiny crack that initiates or nucleates. Okay, the next stage is the crack gradually propagates. Okay, and finally there will be a sudden fracture. Okay, because there is a point where you have less cross sectional area, and that will lead to the failure of the material, and that is why you have fatigue failure.